Imagine spending weeks architecting the perfect SAP BTP environment. You've negotiated all the requirements with the security team, you've aligned with the application developers, and you've finally written the Terraform code that deploys your entire foundation.
Right, the dream scenario.
Exactly. Everything is running beautifully in production. But then a few months later, you decide to do some basic housekeeping. You want to clean up your code, maybe move some text into a new folder just to make it look a bit neater.
Yeah.
So you run a simple Terraform plan just to validate the syntax. And there it is. The terminal flashes red. Plan 5 to destroy.
Oh, man, it's the kind of terminal output that makes your blood run cold.
It really is. You are literally seconds away from accidentally wiping your entire production environment. I mean, deleting the data in a database, severing the connectivity to your on-premise systems, destroying all user access, all just because you moved a few lines of text into a new directory.
It's trying to be tidy, yeah.
Right. So welcome to this deep dive into advanced infrastructure as code for SAP Business Technology Platform. If you are listening to this, I want you to treat it as your senior level engineering study guide. Grab a notebook, open your IDE, because we are getting punishingly technical today.
We really are.
I'm approaching this whole thing from the perspective of a senior SAP enterprise architect. So my job is to look at the landscape design, the structural logic, the dependencies within the BTP ecosystem, and really the enterprise risk of the code we write.
And I'll be coming at this from the perspective of the lead engineer. My focus is entirely on the execution side of things. So when you architect a solution, my job is to translate that into the precise HashiCorp configuration language, or HCL.
The actual nuts and bolts.
Exactly. We'll be walking through the exact command line interface inputs, the directory paths, how to safely manipulate the state file, JSON, and the strict syntax required to make this architecture a reality without causing a catastrophic outage in your production environments.
Which is the goal, right? No outages. So our objective today is critical. We are taking a Terraform setup that works perfectly fine for a day one provisioning scenario, like where you just want to get a single SAP BTP subaccount up and running, and we are transitioning it into a mature day two operational state.
Because day one is easy, day two is where the pain starts.
Absolutely. In a global enterprise, you don't just deploy once, you deploy hundreds of subaccounts. You have dev, QA, pre-prod, and prod for finance. You have the same for HR, the same for supply chain.
Right.
That means we have to extract monolithic configurations into reusable modules. We have to scale our data inputs using declarative loops. And finally, we have to execute a clean reverse dependency teardown when an environment eventually reaches its end of life.
Specifically, for this deep dive, we are analyzing the technical mechanics from Unit 4, applying advanced Terraform concepts. We are drilling into the core engineering task of extracting reusable logic and iterating over lists using meta-arguments.
So if you want to survive this, you need to deeply understand the underlying mechanisms of your main.tf file, your variables.tf file, and honestly, most importantly, the mathematical matching engine sitting inside your .terraform.tf state file.
Yeah, the state file is everything.
It really is. So let's start by evaluating the architecture we currently have. Our current SAP BTP Terraform configuration is basically a monolith. From an architectural perspective, our main.tf file has become this massive, bloated, single point of failure.
Oh, I've seen these. They get huge.
Right. It is packed with basic service entitlements, application subscriptions, service instance creations, just all dumped into one giant file.
It is the classic day one trap. You start with a blank main.tf. You define your SAP BTP provider block. You use the BTP subaccount resource to create the subaccount. And that takes, maybe 10 lines of code?
Barely anything.
But then the requirements start rolling in. The operations team says, hey, we need the SAP alert notification service. So you add a BTP subaccount entitlement block. Then the developers say they need SAP build process automation. So you add a BTP subaccount subscription block. Then you need the destination service, the connectivity service, XSUAA. And before you know it, you have a 500-line main.tf file that is completely hard-coded and rigidly coupled to one specific subaccount GUID.
And from an enterprise architecture perspective, this completely violates the DRY principle. Don't repeat yourself, Think about the BTP global account structure for a second.
Yeah.
We need baseline services. These are the entitlements that every single sub-account in an organization must receive by default.
Yeah, the non-negotiables.
Exactly. Why does it matter that these baselines are isolated? Because it enforces absolute consistency. When your chief information security officer mandates that every single sub-account in the global organization has to have the audit log viewer service enabled, you cannot be in a position where you are just copy-pasting that HCL block into 50 different directories.
Because the moment you copy-paste code across 50 directories, you have instantiated technical debt on a massive scale. If SAP updates the service plan for the audit log viewer, or say you need to switch from a standard plan to a premium plan, you now have to perform a manual find and replace operation across 50 different main.tf files.
Which is terrifying.
It's an operational nightmare. It introduces human error immediately, and it basically guarantees that you will experience configuration drift, where one environment is running a different security baseline than another because someone missed a file.
Okay, I have to push back here, though. In traditional application programming, like if I'm writing Java or Node.js, I achieve DRY by extracting reusable logic into functions or classes. I pass arguments to those functions, and they execute procedural logic.
Sure.
But infrastructure as code with Terraform isn't procedural. It is declarative state. We aren't writing a bash script that just runs line by line. We are defining a structural template. So my worry is that abstraction introduces opacity. Well, if I bury all my sub-account entitlements in some remote function, a junior developer looking at the root main.tf has no idea what is actually being deployed. Are we just creating black boxes and trading code repetition for operational blindness?
That is a very valid architectural concern, but I think it misunderstands how Terraform handles abstraction. We aren't creating a black box, we are creating a defined contract. In Terraform, the equivalent of a function is a module.
Okay.
A Terraform module is simply a container for multiple resources that are deployed together. It allows you to package a set of declarative resources, define strict input variables, which essentially act as the required parameters of your contract, and emit output values.
So it's still declarative.
Exactly. The root main.tf doesn't become blind, it becomes an orchestrator. When a junior developer reads the root file, they shouldn't need to see the 40 lines of JSON configuring the exact parameters of an alert notification instance.
That makes sense.
They just need to see a module block that says module, quote, security baseline, unquote, and know that the standardized corporate security baseline is being applied right there.
So we are moving from writing raw infrastructure to assembling standardized building blocks. I like that. If I'm looking at this architecturally, our goal is to perform a surgical extraction. We need to rip the baseline entitlements out of the monolithic file. But where do they physically go?
This is where we get into the execution. First, you open your terminal and navigate to your root directory, which for this scenario is the BTP directory containing your monolithic main.tf. We need to create a completely new directory structure specifically for these reusable components.
Okay, what's the command?
In your CLI, you run mkdir space-p space modules /service_baseline.
The naming convention there feels very deliberate. You didn't just call it entitlements. You called it modules and then a generic service_baseline.
Correct. At the root level, you create a directory called modules. Inside that, you create service baseline. This taxonomy is highly intentional. In an enterprise rollout, you won't just have one module.
Right, you'll have dozens.
Yeah. Later, you will likely add module/HANA database cluster or module/integration suite tenant. You are building a localized library of standardized enterprise patterns.
So if I'm thinking about how the Terraform engine actually parses files, that new service baseline directory is currently completely empty. It's a void. It needs structure. I assume we need to give it the same basic skeleton as a root directory.
Precisely. You navigate into modules/service baseline and create two critical files. First, service_baseline.tf. This will hold the core declarative logic, so the actual resources themselves.
And the second file.
Second is variables.tf. This is the API boundary of your module. It defines the input parameters required to make the module dynamic.
Let's execute the extraction then. What exactly are we cutting out of the monolith?
You open your root main.tf. You highlight all the resource blocks related to the baseline entitlements. For example, the BTP subaccount entitlement block for the alert notification service, and perhaps the BTP subaccount subscription block for SAP build process automation.
You literally just cut them.
Cut those blocks completely out of the root main.tf. Your root file suddenly becomes much, much shorter. You paste those blocks directly into the new service_baseline.tf file inside the module directory. Then you save both files.
Structurally, we've moved the text. But Terraform doesn't just read text. It communicates with cloud APIs via providers. In this case, it's talking to the SAP BTP control plane via the BTP provider.
Right.
So if we've just dropped raw HCL code into a completely isolated, nested directory, how does this new module know how to authenticate or even construct the API calls to BTP? It's completely disconnected from the provider block in the root file.
That is a critical point, and it brings up the required providers rule. A module in Terraform must explicitly declare which providers it requires to function. It doesn't just automatically inherit the provider configuration in a way that allows it to guess what version of the API it should talk to.
So we have to declare it again.
Yeah. At the very top of your new service baseline.tf file, you must add a Terraform block. Inside that, you nest a required providers block specifying the source of the BTP provider, specifically SAP/BTP.
Now, this is an architectural debate I see all the time. Do we hard code the exact version of the provider in the module? Say we're using version 1.0.0 of the SAP BTP provider. Do we lock it down right there?
It depends entirely on your consumption model. If you are building a public module to publish on the open source Terraform registry for the whole community to use, you generally define a minimum version constraint, like greater than or equal to 1.0.0 to ensure broad compatibility.
Makes sense for open source.
But in our scenario, internal enterprise development, where you want absolute deterministic behavior across your CI/CD pipelines, hard coding a specific provider version constraint, or utilizing a .terraform.lock.hcl file rigorously is the absolute standard.
Because you can't afford surprises.
Exactly. You want to guarantee that the module will behave exactly as it did when your QA team tested it. You do not want an unexpected provider update from the registry to suddenly change how the BTP API payloads are constructed during a live production deployment.
Okay, so we've modularized the code, the text is moved, the provider is declared, but architecturally, this code is currently dead on arrival.
Oh, completely.
We've achieved the DRY principle, sure, but if a junior engineer actually tries to run that code right now, it's going to fail spectacularly. The new module file is orphaned. It is full of hard-coded references to resources that no longer exist in its local scope.
It is severely broken. If you run the Terraform Valet command right now, the CLI will output a massive wall of red text. The service baseline.tf file has lost all of its context.
Let's look at the mechanics of why that is. When you configure a generic module to act as a baseline, how do you inject the specific sub-account context? How does this generic code know where in the SAP BTP global account it is actually supposed to execute these entitlements?
We have to build the bridge between the root orchestrator and the nested module, and that bridge is the variables.tf file we created inside the module directory. We open modules/service baseline/variables.tf and define the mandatory input constraints.
Okay, what do we need?
For this specific baseline, we need to declare 3 variables: subaccount id, project name, and project stage.
Yeah, subaccount id makes absolute sense. The BTP API requires a target GUID, a globally unique identifier, in the payload to know which specific subaccount is receiving the alert notification entitlement. But why project name and project stage? What architectural purpose do they serve inside an infrastructure entitlement module?
They serve as strict governance and operational purpose. They are required to construct the dynamic service name prefix.
For naming conventions.
Exactly. In a mature Day 2 enterprise scenario, you do not just manually name a service instance My Database or Test Alert. You programmatically name it based on the environment to ensure unique identification across the global account and to enforce clean billing tags.
Right, because finance needs to know who to charge.
Yes. For example, you want the final string to resolve to something like Finance Prod Alert Notification. Inside the module, we will use a locals block to concatenate the project name and project stage variables into that exact prefix string.
Which means we have a duplicate logic issue, because before we extracted this code, that locals block defining the service name prefix lived up in the root main.tf.
Correct. You must go back to the root main.tf and delete that locals block. That string concatenation logic no longer belongs to the root. It's a localized responsibility of the module now.
Okay, so the variables are declared in the module. But inside service baseline.tf, the HCL blocks we pasted still contain the old hard-coded references. The code probably says something like subaccount id equals btc subaccount.myproject.id, but the resource btp subaccount.myproject doesn't exist inside the module. It only exists in the root.
Right. You have to execute a global find and replace operation inside service baseline.tf. You must find all of the old specific resource references and replace them with the new dynamic variable references.
So swapping the hard-coded bit for the variable.
Yeah, you change BTP subaccount.myproject.id to var.subaccount.aid. This is the exact moment the module becomes truly reusable.
Because it's fully decoupled.
Exactly. It no longer cares how the subaccount was created. It doesn't care if the subaccount was created by Terraform, imported from a manual creation, or generated by some completely other system.
Yeah.
It only cares that a valid 36-character subaccount EID string is passed into its API boundary.
The module is prepped. It is waiting for data. We need to go back up the directory tree to the root main.tf and actually execute the module call to pass that data. How do we construct that execution block?
In the root main.tf, you create a completely new block, starting with the keyword module. You give it a local logical name, for instance, module, quote, service baseline, quote, open bracket.
And we need to tell Terraform where to physically find the module code?
You define the source argument. For this local execution, you set source equals, quote, /modules/service baseline, quote. The / syntax is critical here. It instructs the Terraform engine to look in the local file system relative to the current working directory.
Let's pause on that source argument because I want to elevate this to an enterprise architecture level. The lead engineer just defined a local path, but in a mature DevOps environment with a dedicated platform engineering team, you would never keep your baseline modules in the same Git repository as your environment deployments.
No, absolutely not.
You would decouple them entirely. That source argument could point to a private Terraform registry hosted internally. It could point directly to a Git repository like GitHub, GitLab, or Bitbucket using an SSH URL.
Which is much safer.
And more importantly, you could append a specific release tag to that URL like !ref equals v1.2.0. This is how you achieve true lifecycle governance. The platform team can update the baseline module repository to version 1.3.0, adding new mandatory security tools, and the individual application teams can choose when to bump the version in their main.tf to consume the new baseline.
It prevents unexpected forced upgrades that might break their pipelines.
Exactly. But I assume for our current execution, a local source path is perfectly fine.
Yeah, for this scenario, it's fine. Inside that module block in the root, we now have to pass the variables. We map the module's required input variable subaccount.aid to the actual resource attribute generated in the root module, which is btp subaccount.project_subaccount.aid. We also pass down the project name and project stage variables from the root directly to the module.
Okay, the code is completely wired up. The root orchestrates, the variables flow down, the module executes. Architecturally, we are sound. So, what is the CLI execution here? Do we just run Terraform plan to see the changes?
Not yet. If you run Terraform plan at this exact moment, the CLI will throw an initialization error. The Terraform engine parses the root configuration. It sees the module block, but the actual module code hasn't been linked into the engine's working directory yet. Terraform needs to download or structurally link the module first.
So how do we force that linkage? What is actually happening on the hard drive?
You have two options in the CLI. You can run Terraform get. This is a highly specific command that strictly updates module references. It parses your source arguments and pulls the module code into a hidden directory called .terraform/modules.
Okay, and the other option?
The other option is you can simply run Terraform init. I strongly recommend Terraform init because it initializes the provider plugins, the backend state configuration, and the modules altogether.
It's just cleaner.
Much cleaner. When you run a unit, Terraform goes to the hard drive, creates or updates the .terraform hidden folder, builds a modules.json manifest file that maps the logical module name to its physical path on the disk, and ensures the entire working directory is fully synchronized and ready for execution.
Okay, the environment is initialized, the architecture is pristine, the DRY principle is satisfied, our root main.tf is incredibly slim, just calling out to beautifully abstracted modules. We feel like engineering geniuses.
We really do.
And this is exactly where we enter the most dangerous part of this deep dive. Because if you run Terraform plan right now, disaster strikes.
It is heart-stopping the first time you experience it. You run Terraform plan, the CLI calculates the delta, and the output prints in bold red and green text. Plan 5 to add, 0 to change, 5 to destroy.
Let's think about this logically from a systems perspective. We just moved plain text from one file to another. The underlying SAP BTP subaccount hasn't changed. The APIs haven't been touched. The actual cloud infrastructure running in the SAP data center is identical to how it was 10 minutes ago.
Perfectly identical.
So why does Terraform want to burn down our actual cloud infrastructure? Literally issue API delete commands for 5 resources, and then immediately issue API post commands to rebuild them from scratch. I mean, if this was a production 8.0 database cluster instead of a baseline entitlement, Terraform would literally delete the production database, drop all the tables, and spin up a blank one. Why is it behaving so destructively?
To understand this catastrophic behavior, we have to look under the hood at the core mathematical engine of Terraform, which is the state file. I want you to run the CLI command Terraform state list.
What does that do?
This command outputs the exact index of every single resource that Terraform is currently tracking in its internal database.
The state file. The .terraform.tf state file. It's essentially Terraform's absolute source of truth. It's a massive JSON document that maps the declarative HCL code to the real-world infrastructure.
Exactly. And the crucial mechanism here is how it tracks those resources. It tracks them by their address in the configuration. Before our surgical extraction, the address for the alert notification entitlement was simply BTP subaccount entitlement.alert notification.
Right, because it was in the root.
That's exactly how it was written in the root main.tf. Terraform recorded that address alongside the physical BTP resource ID in the state JSON. But because we encapsulated those entitlements into a module, their structural configuration address has fundamentally changed.
Because it's nested now.
Right. The new address is module.servicebaseline.btp subaccount entitlement.alert notification.
Ah, I see the delta. Terraform operates by comparing the HCL files on your disk to the JSON state file. It looks at the new HCL and says, hey, I see a completely new resource declaration called module.servicebaseline. I've never seen this address before, so I need to execute an API poster call to create it.
Yep, that's the 5 to add.
And then it looks at the state file and says, well, I have a historical resource recorded as BTP subaccount entitlement, but when I scan the HCL code, it's missing. The developer must have deleted that line of code. Therefore, I need to execute an API delete call to destroy it.
Precisely. That's the 5 to destroy. The Terraform engine is fundamentally blind to your human intentions. It does not analyze the context of your refactoring. It only sees strings. It sees addresses.
It's just doing math.
Just math.
Oh.
It sees a missing address, which mathematically triggers a destroy operation. It sees a new address, which mathematically triggers a create operation. It has no idea that it's the exact same physical BTP entitlement sitting in the cloud.
This is the state drift trap. Our configuration has violently drifted from our state, so how do we fix this? How do we intercept this catastrophic execution plan before it wipes our environment? Historically, this used to be an absolute nightmare for DevOps teams, right?
Oh, it was awful. Before Terraform version 1.1, the only way to fix this was imperative state manipulation. You had to use the CLI command Terraform state env.
Right, I remember that.
You would literally type out the old address and the new address in the terminal and force the state file to update. The problem was that this was a manual imperative action.
Which breaks automation.
Completely. If you had a CI/CD pipeline, the pipeline would just run Terraform apply on the new code and destroy everything because the pipeline didn't know it was supposed to run Terraform state env first. It broke the entire paradigm of declarative infrastructure.
So what is the modern declarative solution?
We explicitly program the state migration directly into the code using a moved block. The move block is an HCL meta argument that allows you to tell Terraform's state engine, hey, I refactored this code. Do not destroy the resource in the cloud. Just rename its address in the state JSON.
We are essentially writing a routing table for the Terraform execution engine. How do we structure this?
You create a new file in the root BTP folder. Let's call it move.tf. Inside this file, you will write a distinct moved block for every single resource that was relocated during your refactoring.
So if we moved 3 entitlements, 1 service instance, and 1 app subscription, we need 5 separate move blocks.
Yes. The syntax is incredibly straightforward, but it requires precision. You write moved, open brace. On the next line, you define the origin address, so from equals BTP subaccount entitlement.alert notification.
Okay.
On the next line, you define the destination address to equals module.servicebaseline.btp subaccount entitlement.alert notification. And you close the brace. You explicitly map the old root address to the new module nested address. You do this for all 5 resources.
Once we've written this routing logic, how do we validate that we've successfully intercepted the destroy API calls?
You follow standard validation procedures. First, run Terraform FMT to ensure your HCL spacing and indentation are correct. Then run Terraform validate to check the syntax for typos. And then, the moment of truth, you run Terraform plan again.
What exactly does the CLI output look like this time?
The output will show a completely different Much more comforting message. Instead of the terrifying 5 to add, 5 to destroy, the CLI will explicitly indicate that it plans to move the resources within the state file.
That's a huge relief.
Yeah, the text will show the old address pointing to the new address with a little arrow icon. The final summary at the bottom of the terminal will say, plan, 0 to add, 0 to change, 0 to destroy. It explicitly guarantees that absolutely 0 API calls will be made to mutate your actual SAP BTP infrastructure.
It successfully intercepts the API calls. But we aren't done yet, right? A plan is just a calculation.
Exactly. Once you confirm the plan is clean, you must execute the Terraform apply command. Even though no physical cloud infrastructure is changing, the apply execution is mathematically required to finalize the address changes and actually rewrite the .terraform.tfstate.json file on your disk to reflect the new structure.
So you still have to pull the trigger.
Yeah, you type yes to confirm, and Terraform silently updates the JSON.
Now, from an operational governance standpoint, I want to discuss the lifecycle of that moved.tf file. We wrote this code to fix a temporary refactoring issue. After you run the apply and the state file is updated, what do you do with the move.tf file? You don't want it cluttering your Git repository forever.
Right. It is fundamentally a transitional file. I strongly advise keeping the move.tf file committed in your Git repository temporarily, perhaps for 1 or 2 sprint cycles.
Why keep it at all?
Because you want to ensure that every other engineer on your team pulls the updated repository, runs Terraform apply locally or in their respective pipeline branches, and successfully migrates their state references too.
Oh, because their local state files still have the old addresses.
Exactly. Once you are operationally confident that the state file for every environment, dev, QA, prod, has been permanently updated with the new addresses, then you can safely delete move.tf in a future commit to keep the repository pristine.
And what is the risk of deleting it too early?
If you remove the move.tf file too early, and a colleague who hasn't updated their environment runs an apply with an older state file, Terraform will fall back to its default behavior. It won't see the writing table, it will see a missing address, and it will immediately try to destroy the resources.
Wow, so leaving the file in place for a sprint acts as a safety net.
A critical safety net, yes.
That is a vital operational insight that separates theory from enterprise practice.
Okay, we've mastered structural modularity and state file manipulation. Let's shift gears and dive into scaling data execution with meta arguments, specifically the for underscore each loop.
This is where it gets fun.
Right. We are moving from organizing code to generating infrastructure dynamically. Let's establish a new enterprise scenario. You have your baseline module deployed perfectly across 50 subaccounts. But now the global security team comes down with a new mandate. Every single subaccount must have multiple specific users assigned as emergency administrators. In SAP BTP terminology, these users need to be assigned the subaccount administrator role collection. This is a very common day 2 requirement. You have a rotating on-call support team, and you need Jane and John to have God mode access to the subaccount in case of a critical outage, but you need to manage that access strictly via code.
Right. Now, here is where my architectural alarm bells go off. If Terraform is strictly declarative, meaning one HCL resource block equals one physical infrastructure asset, adding multiple users usually means copying and pasting the BTP subaccount role collection assignment resource block over and over again.
Which we know is bad.
Yes. One HCL block for Jane, one HCL block for John, one for whoever else joins the on-call rotation. That completely violates the DRY principle we just spent 20 minutes establishing. It makes the main.tf massive again. So how do we introduce programming loop logic without turning our declarative architecture into an imperative procedural script?
We leverage HashiCorp configuration language meta-arguments. These are special constructs built directly into the Terraform core engine that stretch the boundaries of declarative logic.
Like what?
Well, we actually mentioned one earlier, the depends underscore on meta-argument, which allows you to manually force an execution order by overriding the dependency graph. But for scaling data dynamically, we use the canarration argument for underscore each meta-argument.
So for each acts as a multiplier. It allows a single declarative resource block to generate multiple identical infrastructure assets based on a collection of input data.
Exactly. Let's walk through the exact actionable steps for implementing this loop. First, we need to define the data collection. Open the BTP directories variables.tf file, create a completely new variable block named subaccount emergency admins, set its type to a list of strings, and give it a default value of an empty list. written as default equals open bracket, close bracket.
Why default to an empty list? Why not just make it a required variable?
It's a safety mechanism. If someone deploys the configuration without providing a specific data file, the for each loop will iterate over an empty list. The mathematical result of looping over 0 items is 0 resource creations. It simply skips the block.
Makes sense.
If you didn't provide a default, Terraform would crash and throw an undefined variable error, breaking the pipeline. Next, we separate our data from our logic. Open the terraform.tvars file. This is your variable definition file. Assign a list of string emails to the variable. For example, subaccount emergency admins equals bracket quote Jane at test.com quote, comma quote John Doe at test.com quote bracket.
Okay, the data is staged. Now we need to write the logic that consumes it.
In your main.tf, you create a new resource block calling the provider API resource quote BTP subaccount role collection assignment quote emergency admins quote open brace. Inside this block, right at the top, you inject the meta argument. But you cannot just write for each equals var.subaccount emergency admins.
Why not?
You must wrap it in a specific HCL function. For each equals to set, open parenthesis, var.subaccount emergency admins, close parenthesis.
Stop right there. This is where engineers get tripped up constantly. We specifically define the variable in variables.tf as a list of strings. Why do we have to wrap it in a toSet function? What is the structural logic here? Why won't for each just accept a list?
This is a deeply critical mechanism regarding how the state file works. For each only accepts sets or maps, it fundamentally rejects standard lists. To understand why, we have to look at how a list is mathematically structured. A standard list is an ordered collection of items indexed by integers 0, 1, 2. Jane is at index 0, John is at index 1.
Okay, that seems standard.
It is, until you try to track state with it. Let's imagine Terraform allowed lists, and you use the older count meta argument, which does use integer indices. In the state file, Terraform would track Jane as emergency admins bracket 0 bracket, and John as emergency admins bracket 1 bracket.
Okay, I'm following.
Now imagine Jane leaves the company. You delete her email from the terraform.tvars list. What happens to the math?
The list recalculates. Jane is gone, so the item at index 1, which is John, shifts down to fill the void at index 0.
Exactly. And what does Terraform see when it compares the code to the state file? It sees that the resource at index 0 used to be Jane, but is now John. It thinks you want to fundamentally modify the resource at index 0.
Oh, no.
Then it sees that index 1 is suddenly missing entirely. So it executes an API call to overwrite index 0 with John's data, and it executes an API delete call to destroy index 1. Because of a simple shift in an array, Terraform initiates a chaotic destroy and recreate cycle for users who haven't even changed.
That is terrifying.
If this was a list of 50 databases, you would cause a massive global outage just by deleting the first database in the list.
So the state file requires an immutable, unique identifier for every generated resource, completely independent of its order in a file.
Yes, and that is exactly what a set provides. A set is an unordered collection of mathematically unique values. By wrapping our list in the toSet function, we convert the list of emails into a set. Terraform ignores indices entirely.
So it tracks the string itself.
It takes the string value itself, Jane at test.com, and uses that string as the unique tracking key in the state file. If you remove Jane from the set, her key disappears, and Terraform deletes her access. John's key, John Doe at test.com, remains completely unaffected. No shifting, no cross-contamination.
That is brilliant engine design. So inside the resource block, how do we actually extract Jane's email string from the set and pass it to the BTP provider's username parameter?
When their for each loop executes, it dynamically generates a temporary object in memory called each for every item in the set. Because we are using a set of simple strings, the each.key and each.value properties are identical.
So they just output the email.
Yeah, so you write username equals each.value. You also hardcode the role collection name equals, quote, subaccount administrator, quote, and pass the subaccount id as usual.
Let's trace this back to the state file. When we run Terraform apply, what happens on the hard drive?
Terraform reads the single HCL resource block, parses the funds for each containing the 2 distinct emails, and calculates that it needs to make 2 completely separate parallel API POST requests to the SAP BTP control plane.
2 API calls from 1 block of code.
Exactly. If you run Terraform state list afterward, you will see how it immutably tracks them. It won't just say BTP subaccount role collection assignment dot emergency admins. It will append the unique set key in brackets. You will see emergency admins bracket quote Jane at test.com quote bracket as one tracked resource and a separate entry for John Doe at test.com.
It creates one logical block in code, but multiple highly distinct infrastructure assets in the state file. It is the perfect marriage of DRY principles and dynamic scaling.
It is. But as a lead engineer, I have to inject an enterprise architectural caveat here. While we are directly assigning individual human emails to a role collection for the sake of learning this specific Terraform mechanism, enterprise security best practice mandates a completely different approach.
Really? Like what?
You should almost never assign individual users directly to infrastructure role collections using Terraform code.
Why? If the code scales dynamically, what's the issue?
State churn. People change roles, they get promoted, they leave the company, or they change their legal names. If you manage human identities in Terraform, your infrastructure engineers will be running constant pull requests and Terraform apply jobs every single day just to manage user onboarding and offboarding.
Oh, I see. It ties the infrastructure lifecycle directly to the HR lifecycle.
Precisely, and you don't want that.
So what is the correct architectural pattern?
You map groups, not users. You connect your SAP BTP subaccount to a corporate identity provider, an IDP, like Microsoft Entra ID or SAP Cloud Identity Services. Then in your Terraform code, instead of using the username parameter, you use the group name parameter to assign an entire IDP group, like say BTP Global Admins, to the role collection.
And the IAM team handles who is in that group.
Exactly. The membership of that group is managed externally by the IAM team in Azure AD. Terraform simply maps the group to the role once, and your infrastructure state remains perfectly decoupled from daily human churn.
That is a vital distinction. Managing cloud infrastructure is fundamentally different from managing identity lifecycle. Okay, we've built the monolith, we've surgically extracted it into modules, we've fixed catastrophic state drift with routing blocks, and we've scaled our deployments with dynamic loops. This brings us to the final phase of the architecture lifecycle management and the systematic teardown.
The most destructive, yet mechanically satisfying part of the job.
As an enterprise architect, I have to account for the end of an environment's life. We spend all this time building complex, highly nested structures. But if this is a developer sandbox, a QA training environment, or maybe a CI/CD integration branch that spins up to run automated tests, leaving these resources running permanently incurs massive, unnecessary costs.
It gets expensive fast.
Very fast. SAP BTP services are strictly metered. If you leave a WENS Aeon Cloud instance or an integration suite tenant running over the weekend for a pipeline that finished its tests on Friday afternoon, you are burning thousands of dollars of enterprise budget for absolutely zero value. The architecture must account for an elegant, automated, and absolute teardown.
And executing a teardown at scale is rarely as simple as just clicking a single delete button in a UI.
Exactly. Let's use an analogy that fits the engineering reality. Decommissioning cloud infrastructure is like decommissioning a skyscraper in a dense city. You can't just dynamite the concrete foundation if the plumbing, the power grid, and the internal elevators are still active and connected to the city mains.
No, the city wouldn't like that.
The physical laws of the city won't allow it. Similarly, the cloud APIs will reject your commands. If you try to issue an API delete call to the subaccount while an application is still actively subscribed to a database service inside it, the SAP BTP API will throw an HTTP 409 conflict or a 400 bad request error. It will refuse the deletion because of active downstream dependencies. So, how does the Terraform engine mathematically handle the destruction of a deeply nested multi-provider SAP BTP environment?
It relies entirely on graph theory. Specifically, the Terraform engine calculates a directed acyclic graph, or a DAG. When you run Terraform Apply to build an environment, Terraform parses all of your HCL code and builds a mathematical map of vertices and edges.
It's like a huge web of connections.
Yeah, it calculates the exact dependency chain required to build from the ground up. It knows mathematically that it must create the subaccount GUID before it can create an entitlement, because the entitlement API payload requires the subaccount GUID to function.
It automatically maps out the foundation to roof construction sequence.
Exactly. When it comes time to tear it down, you use the CLI command terraform destroy. Technically, this is just an alias for terraform apply-destroy. When you execute this, Terraform doesn't just randomly start deleting things. It loads that exact same directed acyclic graph into memory, but it walks backward up the dependency tree.
It reverses the graph.
Yes. It identifies the leaves of the graph, which are the resources with absolutely zero downstream dependencies, like the roof of your skyscraper, and it issues delete calls for those first. Once the API confirms they're gone, it moves down to the walls, the plumbing, and finally it destroys the foundation.
But the specific architectural scenario we are working with today is highly complex because we are utilizing a multi-provider setup. We have the standard SAP BTP provider managing the sub-account, the entitlements, and the role collections. But nested inside that sub-account, we have an entirely separate environment. A Cloud Foundry org, managed by the Cloud Foundry provider, deployed from a completely different directory in our repository.
Yes. And this multi-directory, multi-provider structure strictly dictates our execution order. Because Terraform state files are logically isolated per directory, the state file sitting in the BTP directory has absolutely zero awareness of the state file sitting in the Cloud Foundry directory.
They are blind to each other.
Completely blind.
Oh.
If you just jump into the BTP directory and run Terraform destroy, Terraform will try to delete the subaccount. But the BTP backend API will hang, timeout, or throw a hard error because it knows that a Cloud Foundry space, active routes, applications, and CF-level service instances still exist inside that subaccount boundary.
So we cannot rely on a single DAG. As engineers, we have to act as the higher-level orchestrator across the different directories. What is the exact sequence of commands?
We have to strip the interior of the skyscraper first. Step 1, you must open your terminal and navigate explicitly into the Cloud Foundry directory. You execute Terraform destroy. Terraform calculates the reverse DAG to delete the inner CF space, the application routes, the app deployments, and the CF-level service bindings.
And it asks for confirmation.
It calculates the plan and prompts you for confirmation. You type yes. Terraform executes the API calls, completely purging the inner-nested environment.
And once the terminal confirms that the Cloud Foundry space is completely eradicated, that frees up the dependencies on the parent subaccount.
Exactly. Step 2. Once the CF destroy is 100% complete, you navigate up and over to the BTP directory. You run Terraform destroy again. Now, Terraform loads the BTP DG and calculates the reverse path for the foundation.
What goes first in that one?
It will first destroy the emergency role collection assignments we generated with our for each loop. Then it will issue API calls to destroy the app subscriptions and service instances. Then it will revoke the entitlements. And finally, as the absolute last step, with all dependencies cleared, it will issue the final API call to delete the subaccount itself. You confirm with yes, and the engine goes to work.
I want to emphasize a critical reality regarding these destroy operations. They are not instantaneous. When you run destroy on a massive BTP environment, it doesn't take 3 seconds. While the Terraform CLI is running in the terminal, what should an engineer be doing to verify the system isn't just hanging?
You should be verifying the deletion progress live out of band. I highly advise logging into the SAP BTP Global Account UI, the cockpit, in your web browser.
While the terminal is running.
Yeah, while your terminal is polling, you can watch the UI. You will literally see the subaccount status change from active to a yellow dilution in progress state. Destroying deeply nested environments, releasing massive compute quotas, and deleting databases can take several minutes due to the asynchronous nature of the BTP backend microservices.
So the terminal is just waiting.
Terraform is essentially sitting in a while loop, polling the BTP API every few seconds, waiting for a 200 OK or a 404 not found HTTP confirmation before it is mathematically allowed to proceed to the next step in the day. So if your terminal sits there for 4 minutes saying, quote, still destroying, unquote, do not hit Stral+C. Be patient. Let the engine do its job.
Because if you hit Stral+C during a destroy, you risk corrupting your state file while the cloud provider is still processing the deletion in the background, which leads to horrific phantom resources that are incredibly difficult to clean up.
You end up with a fragmented state.
Exactly.
Let the day finish its execution.
This brings us to the culmination of our deep dive. What a massive, highly technical engineering journey. We started with a static, monolithic, hard-coded configuration that violated every enterprise architecture principle, and we transformed it into a dynamic, highly scalable, enterprise-grade architecture.
We really covered a lot. We explored the mechanics of encapsulation by extracting day one code into reusable modules, passing dynamic context across boundaries via variables. We learned how to safely interact with the Terraform JSON state file using HCL-moved routing blocks, intercepting catastrophic resource loss, and API deletions during structural refactoring.
We scaled our data inputs dynamically, migrating away from the dangerous index shifting of lists by using the for each meta argument and the toSet mathematical function to generate multiple, uniquely tracked infrastructure assets from a single declarative code block. And finally, we managed the lifecycle, orchestrating a clean, graph theory-based reverse dependency teardown across isolated multi-provider directories.
For those of you who want to put hands on the keyboard and you really must execute these CLI commands yourself to truly internalize the state mechanics, I strongly direct you to explore the official SAP samples repository on GitHub.
Where can they find that?
Go to github.com/sap-samples/btp-terraform-samples. You can view these exact configurations, clone them to your local machine, and practice the modular extraction, the state routing moves, and the multi-directory teardowns in your own BTP trial account.
It is honestly the only way to truly understand the mechanics before you attempt this on a production landscape. Okay, before we sign off, I want to leave you with a final architectural puzzle to chew on. Today, we have achieved mastery over local modules, local variables, and most importantly, local.terraform.tfstate files sitting right there on your laptop's hard drive.
The local setup.
Exactly. But what happens when you scale beyond a single engineer? What happens when your entire platform engineering team, say 5 developers and 3 DevOps engineers, all need to collaborate on this exact same BTP subaccount simultaneously? If every engineer has their own isolated .terraform.tfstate file on their local laptop, whose file is the source of truth?
That is a recipe for state collision, a disaster waiting to happen.
You need to start looking into remote state backends. You need to investigate how to store that JSON state file in a centralized Amazon S3 bucket, or Azure Blob Storage, or Terraform Cloud, complete with DynamoDB state locking to prevent concurrent executions from corrupting the file.
State locking is vital.
And more importantly, you need to understand drift detection, because when an application administrator bypasses your pipeline, logs directly into the BTP cockpit UI, and manually changes a critical security setting without telling Terraform, how will your code know who is telling the truth? How do you mathematically reconcile the declarative HCL in your repository with rogue manual changes in the real world?
That is exactly where Day 2 operations evolve into Day 3 mastery.
Exactly. The architecture never stops evolving. Until next time, keep exploring, keep building, and keep ruthlessly questioning the state of your infrastructure.